Hello everybody, thank you for being there. So I'm Louis Duvivier. I'm doing a thesis in Lyon with Rémy Cazabet and Céline Robardet, and I'm going to present you graph spaces, which is a framework to assess the relevance of statistical graph models with respect to a given graph, using both probability distribution and geometric properties for this purpose. So to introduce the context, what I mean by a statistical graph model is a way of modeling a graph by assuming that its structure is defined by some important properties and that it is otherwise random. So to take some examples, the most known one is the R-Rémy graph, which defines the number of nodes and the number of edges, and then constructs the graph at random. But the configuration model can also be seen as such a statistical graph model, because you set the degree distribution and then edges are drawn at random respecting this degree distribution. Stochastic block model is the same, with the constraint that the number of edges within each group defined must be respected. So in all these situations, there are some important properties that are fixed in advance, and everything else is random. And one can wonder, with respect to a given graph, what is the best such model? Which are the properties which explain best the structure of edges? And to be even more specific, one even more typical question is to find the best decomposition in communities. It can be seen in the case of stochastic block model as such a choice. But those are only some questions that one could ask using those statistical graph models. So after explaining the motivations of this framework, which is graph spaces, I will present various properties they have and why it is interesting, focusing on 3 examples. So once you've defined the properties you want to work on, what comes naturally is to study the set of all graphs which respect those properties. The set of all graphs which can be generated using the model under study. This is what I call omega m. And I want to say right at the beginning that I will be considering multigraphs with self-loops authorized. This is for the sake of simpler computations in the following. And once you've defined this set, you can define the probability to generate the graph under study with respect to this model, if you consider the uniform probability distribution. And this is what would be the likelihood of the model, which is a traditional way of choosing a model in statistical analysis. And this is, for example, what is done in this paper, and this is a methodology that has been developed in the case of stochastic block model by Peixoto, for example. One limitation of this approach, and at least something that may be counterintuitive, is that if we consider those 3 multigraphs, they all belong to the same set, if we consider the R-Rémy model, because they all have 8 nodes and 10 edges. I want to stress that this is a multigraph, so there are 10 edges on a single link. And yet, one would say that the one at the right looks a lot more like a random graph than this one. But the likelihood is the same, because the set of all graphs, the set is omega of R-Rémy with 8 nodes and 10 edges. The set is the same, so the cardinal is the same, the probability is the same. So this is one limitation of the likelihood per se. And to talk a bit about for geometric properties now, another point of view on this set of graphs can be to look at the barycenter of the model. And what I mean by the barycenter is we have multigraphs, and so we can compute the expected value for the weight of each edges and consider the graphs whose weight is this expected value. And this is, in some sense, the barycenter. If you consider the graphs as vectors, we are computing really a barycenter. And to show that it is not a pure construction, if we do that in the configuration model, this is the value we obtain, and actually this is the value which is used in the modularity function. So modularity basically compares the actual weight of edges within communities with the theoretical weights of this graph barycenter. And here too there are some limitations, and it has been shown in this paper that the modularity can find communities even in random graphs. This is illustrated here. This is the same adjacency matrix, but on the right, it has been reordered in order to show the partition of maximum modularity, and we see that we can actually observe communities where there are not. And this is due to random fluctuations in the generative process. And so what I want to explain is that if we focus only on the probability distribution, like in the likelihood, or only on the geometric properties, we observe that we have some limitation in both cases. And this is why we want to take both into account at the same time. So with this, looking at the set with both a probabilistic structure and the geometric structure, which in this case I define using the normalized edit distance, which is basically the fraction of edges between two graphs that do not overlap. So if the distance is between 0 and 1, 0 meaning that they have no edges in common, 1 meaning that they have all their edges in common. So to enter in the subject, in the topic, the first thing we looked at is about the shape of this graph space. And here, what we compute is for different model, R-Rémy, and configuration model with different degree distribution, and two stochastic block models. All those models, we choose them such that they have the same cardinality. So the size of the ensemble is the same. And then we compute the expected, the value, the distribution of normalized edit distance with respect to the barycenter. So the fraction of edges which are shared between the graphs in the space and the barycenter. And what we can observe is that for all those graphs, it is superior to 0.45. And in many cases, it is even larger. Meaning that in most cases, they have more than half of their edges which do not overlap with the barycenter. All graphs are very far from the barycenter. And this is a situation which can be thought as a sphere. Meaning that we compute a barycenter, and everything in the space is very far from it, just as the center of a sphere. And what does that mean? It means that the barycenter is actually not representative of the set. And this could be a part of the explanation why modularity has a difficulty on capturing those the information we look at, because it focuses on this barycenter. On the other hand, once we've said that, we can, if we have a graph and we want to compare it with all of the graphs of the model, we understand that we cannot compare it with the barycenter. But now what we try to do is to compute the expected value of the edit distance between the graph, the understudy, and all other graphs in the model. So this is what we call the edit distance expected value. And now, if we consider again the three graphs that were mentioned before, and we want to assess their position in this graph space. This is what we obtain. What is shown here is the edit distance expected value for the 3 graphs mentioned with an increasing density. So when the density is low, they all have an expected value of around 1, because in this case there are very few edges, and so whatever the type of graph, all graphs in the model are they share no edges. But as the density increases, the Herder-Schreiner generated model, his expected value drops dramatically, meaning that it shares more and more edges with all other graphs in the model. In some sense, it is central. And on the other hand, the graphs whose links are concentrated, whose edges are concentrated on a single link, this one, his edit distance remains around 1, and we can see like that it is in some sense an outlier, that it is exceptional, and that we could not capture with only with the likelihood. And finally, I want to talk about model comparison, because this is one thing that this framework allows to do. And to take an example, I want to talk about the soft configuration model, which is an approximation that was introduced in this paper for the configuration model in order to allow for direct computation of the probability of the weight of an edge being some specific value, because it is really hard to do in the original configuration model. So this approximation was proposed with some relaxations on the assumption made for the configuration model. The problem is that it is not possible. It is hard, and it is not done in this paper to understand exactly what those relaxations imply on the set of all graphs that can be generated. There are more graphs that can be generated, but we don't control exactly what is modified. And what we do is that for some specific degree distribution, here it is an arithmetic degree distribution with a mean degree that increases. We compute for 50 different graphs that were generated using the configuration model, the edit distance expected value in the configuration model and in the soft configuration model. And this is what is plotted here. And we observe that the values are really close. And what does that mean? It means that, on average, the number of edges shared with graphs generated by the configuration model and by the soft configuration model, they are more or less the same, so that the graphs produced by both models look more or less the same. And we can also observe that for a more constrained degree distribution, such as a star degree distribution, the assumption works less well, and so it allows to assess also the limitations of this assumption. So, in order to conclude, I want to sum up the main interest of studying omega n with this double structure is that it allows to first to show that the barycenter is actually not representative of the whole set, to distinguish between typical and outlier graphs in the space, and finally to compare different statistical models. And that we did with the structure I presented in the beginning, but actually what is also rich is that we could have defined other probabilistic and other geometric structure, and it could bring even more information. Thank you for your attention and your invitation.
For the this feature of the spectral distance for the geometrical structure.
What would happen if we considered the No, I have no idea. I know. I mean, I know there are distances that are based on the spectral decomposition of the graph, and it would be interesting to look at it, but we haven't done it.
Does this help or you have some point that it helps in deciding for a given graph, which is the best class of models, to summarize it?
This is what we would like to do. I mean, or at least one possible track for doing so, yes. And for example, this kind of results is what encourages us in this perspective, because yes, one problem with statistical modeling, in my opinion, with statistical modeling is that when we have only one graph, it's not like we have a whole set of graphs. And I mean, many statistical methods rely on the fact that you have many observations, and in this case, we have only one. So it's you need to find like tricks to overcome the problem.
So maybe I'm off topic, but so if I give you a graph, would you be able to use a method like this to find subgraphs that are outliers for some reason? And do element detection in graphs, basically.
In all that we've done for the moment, I mean, for all models considered, and for example, the one I introduced here, one property that is always set is the number of nodes. And in the situation you talk about, I mean, you could imagine that taking the properties, some properties of the whole graph as being the properties of interest, and then looking at the properties of subgraphs and their position in the set. But in this case, the number of nodes would vary, and the problem is that if you allow the number of nodes to vary, your set becomes infinite, because you can consider graphs of arbitrary size. So it modifies a lot of things. I don't know if it's maybe it would be possible to handle, but that would be more work.
When you say statistical modeling of graph, what do you consider as a random variable vector?
The graph. The graph is the random variable, if this is the question.
Yeah. What is exactly the random variable vector? That is the weights of ages or...
Okay, I understand. It is... yes, it would be the weight, the vector of weights. Yeah, sure. I mean, for example, in Rémy, we would consider all vectors of size n whose sum is equal to m, and they would all have this probability of being generated.
So thank you very much for the talk.
Thank you.